Hello, my name is Jeff Bees, and I'm here to talk to you about the Compressible Flow Lab for ME4031 Basic Mechanical Measurements Lab. In this video, we will walk through the experimental setup, and then our procedure will be broken up into 3 cases examining different upstream and downstream pressures, and then we will walk through the expectations we have for results in this experiment. So we'll start out with the experimental setup. Here's what you'll see when you come into the lab. And here's a fluid power schematic of the same setup. I will walk through the setup from upstream to downstream, starting here with the air compressor, which then passes the air into the pressure reducer. This allows you to manually adjust from 0 psi up to the maximum psi given by the pressure gauge. This is connected using a quick disconnect coupling to the pressure gauge, which has another quick disconnect coupling connecting it to the filter. From here it will branch off into 2 different flow meters, each with a different scale. And which flow meter is used will be decided based upon a 2-position 3-way valve given here, where in this case the flow meter on the right will be allowed to pass, meanwhile the flow meter on the left is capped. And if we slide this into position 1, rather than position 2 that it's currently on, then the flow meter on the left will be allowed to pass through while the flow meter on the right is capped. This is again connected with a quick disconnect to the orifice, which is then connected to the vacuum gauge, and finally connected to a variable valve which controls the vacuum pressure of the vacuum pump, which has a power supply attached to it. Now the colored dashed lines that you see here and here correspond to alternate configurations where the upstream pressure can come from ambient through a nozzle, or it can go to ambient through a nozzle. For the upstream conditions, you'll want to make sure to get the barometric pressure reading, which is provided through the eNet software, and you'll want to get the ambient temperature, measured using the thermometer located at the front of the lab near the sink. When the case that you're performing involves the supply air, you want to make sure that the compressed air valve is on, but before you do that, make sure that the pressure regulator is turned all the way down so that there is no flow passing through. You will be able to monitor the upstream pressure using the pressure gauge, which is the gauge to the left of your setup. This gauge reports pressures in units of psi. It is important that you do not exceed the 0 to 25 psi range of the gauge. Even though the gauge reads from 0 to 30, it is important to stay within a 0 to 25 psi range. An important note about safety is that in this experiment you'll be using compressed air at high pressures, and therefore you should check all connections before applying any pressure. As I mentioned before, you will have 2 flow meters, in this case rotometers with full-scale outputs of 50 and 10 SCFH. The reason why you have 2 flow meters is to choose the rotometer that fits the scale that you're measuring within, and therefore you can get a higher resolution when you're below 10 SCFH, but you can still manage to reach higher values when you need higher flow rates. Now, since we're dealing with compressible flow, it is important that you convert all of your flow readings between SCFH and CFH. Remember that the S stands for standard, and that represents the factory calibration conditions from which the rotometers were created with. And then you'll use equation 1 here in order to convert between the flow rate indicated by the rotometer and the actual flow rate that is passing through your system. Downstream of the rotometer is the orifice, which in our setup has a 0.052 inch diameter, and this marks the division between the upstream and downstream regions. The orifice also establishes a choked flow when you reach a critical pressure ratio between upstream and downstream, given by equation 5 here. Now for the downstream conditions, again, you'll want to get the barometric pressure reading from the eNet software. You'll produce a vacuum pressure using the vacuum pump located over here, which has a valve located at the exit of the pump, which allows you to vary the vacuum pressure. You'll want to make sure that the vacuum pressure valve is closed fully before you toggle the on-off switch into the on position. Once you've turned the vacuum pump on, you can open this valve in order to increase the vacuum pressure. It is very important that you check all connections before initiating this experiment. The vacuum pressure generated by the pump can be measured by the vacuum gauge located to the right of the setup. The vacuum gauge uses units of inches mercury rather than the PSI from the other gauge, which means that it has a higher sensitivity due to the scale difference. It is very important that you do not allow this gauge to go below 0. To do so can damage both the vacuum gauge and the vacuum pump. Now we'll talk about the procedure. For each of the 3 cases, you want to make sure to set up the proper configuration, 0 both the pressure and vacuum gauge, and then you want to measure and record the temperature, indicated flow rate, as well as the up and downstream pressures. Case 1 will involve flow from ambient pressure to the vacuum pump, which means the upstream pressure corresponds to ambient pressure, while the downstream pressure is given by the vacuum pressure. Once you've set this configuration up, make sure to check with the TA before running the experiment to make sure that all the connections are correct. Then you'll want to turn on the vacuum pump and vary the vacuum pressure with the ranges and increments given by the lab manual. Case 2 conditions involve the upstream pressure being generated by the supply air and the downstream pressure being equal to the ambient pressure. Now here you want to make sure that the supply air valve is in the on position. Then you want to turn the pressure regulator valve in order to vary the gauge pressure with the ranges and increments given by the lab manual. Now case 3 brings in elements of the previous 2 because the upstream pressure is given by the supply air and the downstream pressure is given by the vacuum pump. With the TA present, turn on the vacuum pump with the valve fully closed initially. Then you'll want to simultaneously turn the pressure regulator and vacuum pump valves towards an increasing pressure so that neither of the gauges drops below 0. Once the vacuum pump valve is fully open, you can set the supply air back to 0 psi. Once the vacuum pump valve is fully open, you want to keep that valve open for the remainder of the experiment. Then you will turn the pressure regulator valve in order to vary the upstream pressure with the ranges and increments given in the lab manual. Now the reason why you need to have the TA present is because it is absolutely essential that you do not allow either the pressure gauge or the vacuum gauge to fall below 0, as it can damage the gauges and or the vacuum pump. Now we'll go into the results. For cases 1 and 2, you'll examine 3 different types of plots. First one's a volumetric flow rate versus the pressure ratio. And by pressure ratio, I mean the downstream pressure divided by the upstream pressure. Remember that these pressures should be absolute pressure. And then you'll want to create a line on this plot to indicate the critical pressure ratio. Then you'll want to do a plot of the mass flow rate versus pressure ratio. And then the last item for cases 1 and 2 is to do a log-log plot of the volumetric flow rate versus the pressure differential. In these plots, you'll want to identify 2 regions, one where the volumetric flow rate is constant, and then the other one where it's increasing with a particular value. Then you'll want to perform linear regression in order to compare each of these cases to what you would expect the slope to be. For case 3, you'll want to construct a summary table indicating the theoretical and measured volumetric flow rate, as well as the calculated discharge coefficient. From this information, you can calculate the average discharge coefficient for your system. That's all I have for you, so I hope that you have found this useful and that you have a wonderful day.